So what we're going to do now is we're going to take a moment and we are going to look at a very specific example, and this example is y equals x to the fourth minus 4x cubed. And using our first derivative test, which tells us local maximums and minimums, and then our second derivative test, which is going to tell us points of concavity and inflection points, we are actually going to be able to describe and graph this with one or 2 points and a very, very good idea of what it's supposed to look like. All right? So the first thing we're going to do is the first derivative. So the first derivative is going to give you
4x to the third minus 12x squared.
4x to the third minus 12x squared. Very good. If you were to factor that, you would have 4x squared times x minus 3. Now we're going to take the second derivative of that function, and we are going to get 12x squared minus 24x. Factor out the 12x, and you have x minus 2. So the first thing we're going to start with is the increasing and decreasing test. All right? So we use the first derivative. We are going to find out all our increasing, decreasing areas. So I'm going to move this up. And we start with the interval from negative infinity to 0, and then from 0 to 3, and then from 3 to infinity. This is another way of writing what we've already written. Instead of writing it in interval notation, we are writing it in interval notation instead of writing it in inequality notation. Okay? So let's look at our factors. We have 4x squared, which is always positive, and then we have x minus 3. From negative infinity to 0, it's negative. From 0 to 3, it's negative, and from 3 to infinity, it's positive. So it has a negative slope, it has a negative slope, it has a positive slope, which means from here to here, we had a local, is it a minimum? Slope was negative, now it's positive. It's definitely a minimum. Very good. So we have a local minimum there at 3. What is our local minimum? Well, you substitute it into the original equation and you get 81 minus 108. What do you get? 81 minus 108 is? Negative 27. Thank you very much. So now we have our local minimum. Have we done a lot of graphing yet? No. But we do know that right here, because it was negative and it stayed negative, it should look like this, right? So I would have some sort of point. That's where 0 is. This is 0 right there. So we actually have a point that technically looked like it was going to be a local minimum or maximum, but it's not, because the slope was negative and it stayed negative. So it went into that critical point negative and left that critical point still negative. So when we did our critical points test, that is not an absolute minimum, that is not an absolute maximum, it is just neither. Now let's look at our concavities. Oh, I didn't mean to do that, sorry. Going to the second derivative test, we have 2 intervals. Well, 3 intervals again. Once again, starting from negative infinity to 0, because of the 12x. We also have from 0 to 2 because of the x minus 2, and then we have from 2 to infinity. So on our second derivative test, we have 12x. From negative infinity to 0, it is negative. From 0 to 2, it is positive, and from 2 to infinity it is positive. We have x minus 2. From negative infinity to 0 it is negative. From 0 to 2 it is negative, and from 2 to infinity it is positive. So what I have on my second derivative test is I have concave up because it's positive. 2 negatives make a positive. Concave down because it's negative. And concave up because it's positive. So now let's bring all this and put it over here for just a minute. So I'm going to make my graph. Quick sketch. How fast does my sketch? Really quick. All right. So 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And according to this, I have a point at 3 and negative 27. So on my x-axis, I'm going to go by 5s, and on my y-axis, I'm going to go by 5s. All right.
Why is it C?
At 0, the value of my function is very easy. Plug it into that original equation, and you will get 0, 0. So remember, we are going by 5, so I'm going to put a 5 there, I'm going to put a 5 there, and that's all the numbers I'm going to put, okay? Everything's by 5s. So at 0, 0, it's there. And it says that going in, 1, it's concave up, and 2, it's a negative slope, so it should look like this. Negative slope, concave up would look like that, right? Is that correct, yes or no?
Yes.
Yeah. Is it a general feature of the graph? Absolutely. Is it an exact feature of the graph? Not quite, but it's where it needs to go. The next function from 0 to 2 says it's concave down. So from 0 to 2, approximately here it's concave down. All right? And at 3 it's at negative 27, way down here. So it's got to come back to concave up. And somehow it's got to get back above the x-axis at some point. But did we get direction as to where it crossed the x-axis again?
No.
No. But I could very quickly factor that out, and I would have x cubed times x minus 4, and I should be crossing the x-axis at 4. So my graph is grossly disparaging, isn't it? But if I were to change this from 5 to, let's say, 2s, how does that sound? How about we put it at 2? Let's make the x-axis, instead of 5, we'll make the x-axis 2. So this point of 3 and negative 27 still works, and it seems to be crossing at 4. So that's a basic idea of what this graph looks like. Now I'm going to jump over to a graphing page, and we're going to take a look at it. So to graph these functions, what do I need to do? I need to, 1, look at the function right off the top of my head, and I should have a general idea of its basic direction. A couple reminders. If the function is an even exponent, function is even, it is going to have endpoints either both pointing up or both pointing down. If it is odd, you will either have it endpoints like that or endpoints like that. Somewhere in the middle, you will have a break in this graph if you have anything higher than a linear function, which we don't really deal a whole lot with linear functions. So the idea is that it ends up to the right and down to the left, or down to the right and up to the left. Okay? So that's your even odd functions. That gives you the basic idea. Then we took our first derivative. Our first derivative gives us our direction of slope and our local maximums, local minimums. If it switches from negative to positive, it's a local minimum. If it switches from positive to negative, it is a local maximum. You can see right here what I'm circling, that we have a local minimum because it switched from negative to positive. Okay? Then we take our second derivative. Our second derivative gives us all concavity points and points of inflection. So the interval to the left and right, if it's concave up, it's positive. If it's concave down, it's negative. You do that by taking the factors and setting them in the interval table. The interval table is right here. 2 negatives make a positive. 2 positives make a negative. Okay?
Positives make a negative?
Sorry, 2 positives make a positive. That's hilarious. Thank you, Jen, for catching that.
5 midpoints?
So we're going to try this next function, and it's f of x equals 4 minus x. I apologize. It's not 4 minus x. Don't write that down. Whatever you do, don't write down 4 minus x. I wrote down the derivative, which is not good. So it's not just the derivative, but x to the 2/3 multiplied by 6 minus x to the 1/3.
What?
We need to take the derivative of this. Anybody see a chain rule occurring here? And a product rule possibly?
Yeah.
So we do the product rule and that gives you something crazy. Or,
We combine them?
well, technically we could combine 1/3 of it.
But
Watch. Ready?
that'd be x to the 1/3.
Wouldn't this be x to the 1/3
6x
times x to the 1/3 times 6 minus x to the 1/3.
Right. Yeah. Whoa.
So wouldn't that technically be x squared to the 1/3? Times 6 minus x to the 1/3?
Yes.
And then couldn't I distribute that through, giving me 1/3 6x squared? It's not 1/3 there, that's ridiculous. 6x squared minus x cubed to the 1/3 power? Could I do that?
Yeah. Guess you can.
I could do that. Do you think that this is going to make it easier?
Yes.
Looks like it.
Because the chain rule is easier than the chain rule is.
All right, well then let's try it. So that would give us 1/3 times 6x squared minus x cubed to the negative 2/3 power multiplied by 12x minus 3x squared. Any part of that confusing? Okay. Then rewriting that, we still are getting this first derivative. We would then have 12x. That's just, this pen is not working today. I apologize for the awfulness. 12x minus 3x squared divided by, remember this 1/3 makes there a 3 in the denominator. 3 times 6x squared minus x cubed to the negative 2/3. Positive 2/3 now, no longer negative. We can then reduce that further. The 12, the 3, and the 3 is going to give us 4x minus x squared divided by 6x squared minus x cubed to the 2/3 power. So doing some basic math, algebra, our final result is going to be 4 minus x over x to the 1/3 power. This is our first derivative, multiplied by 6 minus x to the 2/3 power. That is the first derivative of x. Now we need to take the second derivative of x.
Yeah.
Instead of trying to put it back in this time, or do you want to put it back in again and do the same?
I want to do it.
Well, notice that there was some trickery we had to do at the end. So let's take the second derivative and we will do, reminder, u prime v minus v prime u over v squared. So u prime is negative 1 times x to the 1/3 times 6 minus x to the 2/3 minus, and now we need to find v prime. V prime is going to be tricky because I have x to the 1/3 and 6 minus x to the 2/3. So to find v prime, for this I'm going to do the product rule this time, which is v prime u plus u prime v. So I will have 1/3 x to the negative 2/3 times 6 minus x to the positive 2/3 plus x to the 1/3 times 2/3 times 6 minus x to the 1/3. So I would multiply this first one by 6 minus x to the 1/3 power and the second one by x to the 2/3 to get our denominators alike, and that would give you 6 minus x plus 2x divided by 3x to the 2/3 times 6 minus x to the 1/3. Agreed? Which is pretty insane, right?
Mm-hmm.
if you think about it. I mean, we're getting crazy amounts of information here. So do we want to go back and put it back in and do the chain rule again? Like we did the first time? Sure, why not? Sounds good. So we'll erase all of this. Apparently we're not going to erase any of it because it just doesn't want to erase. Well, some of it did. But we need to find the second derivative of this. We need to find that second derivative. So what we're going to do is we're going to put x to the 1/3 back in. And in order to put x to the 1/3 back in, we have to assume that 6 minus x to the 2/3 is 6 minus x to the 1/3 how many times?
Twice.
That would be tricky. Anybody got any better ideas? Just crazy, right? Sometimes it just takes a long time. So going with what was just stated, if we were to rewrite it like this, 6 minus x squared, this could be to the 1/3 power now. That's back to the original f prime of x. Okay, now that we have it written that way, what we can now do is multiply this out to 36 minus 12x plus 36x, or plus x squared, and then multiply that by x, and what you end up with is x cubed plus 12x
Would it be minus?
minus 12x, thank you, minus 12x plus 36, minus 12x squared plus 36x to the 1/3 power in the denominator, and in your numerator you would have 4 minus x. Then doing the second derivative with the quotient rule, you would have u prime v. U prime v would be -1 times your denominator, and we're just going to put v here just so that we don't have to do too much thought at the moment. And then we're going to put a subtraction sign, and then it's v prime u, so it's going to be 4 minus x times 1/3 times x cubed minus 12x squared plus 36x. That's really awful looking, but I'm trying here. Plus 36x multiplied by the chain rule, which would be 3x squared minus 24x plus 36. All of that divided by v squared, which would be x times 6 minus x squared to the 2/3 power, or this here to the 2/3 power. So it would be x cubed minus 12x squared plus 36x to the 2/3 power. By the way, right there, that is the negative 2/3 power. There's no, I was noticing the exponent was missing. And v right here is x cubed minus 12x squared plus 36x to the 1/3 power. So it just gets big. Does it make it get easier? No, it does not, but it continues to get bigger, continues to get larger, and then you have to do some, it feels like trickery half the time. But you're not doing trickery, all right? It kind of feels like witchcraft, because it's just insane. Would you agree? Now let me show you something very interesting. I can't have this negative exponent in my numerator, right? I need it in my denominator.
Yes.
So I'm going to multiply the numerator and the denominator by x cubed minus 12x squared plus 36x to the 2/3 power. We okay with that?
Say that again?
We're going to multiply it by x cubed minus 12x squared plus 36x to the 2/3 power. when you multiply that to the 2/3 power in the numerator and denominator, so I'm just going to say repeat that there too. Okay? You multiply that, it's going to cancel out this one right here. And what's it going to do to that 1/3 power? It's no longer going to be 1/3, it's now going to be a whole. Right? It's not going to be 1. So that would be numerator negative x cubed plus 12x squared minus 36x minus 4 minus x times 3x squared minus 24x plus 36 divided by x cubed minus 12x squared plus 36x to the 4/3. Everybody okay with that? Over here I'm going to factor this to 3 times. That would be x squared minus 8x plus 12. So it's going to be x squared minus 8x plus 12, which the x squared minus 8x plus 12 factors to x minus 6 and x minus. So I have a 4 minus x here. My first values that I'm underlining right now factored, we knew, to negative of x times x plus 6 squared from earlier. That doesn't seem to benefit us at the moment, does it? So we're going to have to look for other ways to get rid of this stuff. Yes, ma'am. Our very simple error is right here. That should not be a plus, it should be a minus. And now that that's a minus, this is going to actually make it a little bit easier. Because now I can factor out of everything in x minus 6 if I would like to. So as was just noticed, there was a 1/3 here that I just circled, so we put it right there. Okay. Now we're going to factor out this x to the 1/3. This is back to earlier, times x. Hold on. X times x minus 6 squared to the 4/3. So as we are continuing, we can now cancel out this 1/3 here and that 3 there, and they're gone. So I've got 4 minus x, I've got x minus 6, I've got x minus 2, I've got negative x and x minus 6 squared. So this thing just gets convoluted, but we're nearly done, aren't we? Are you starting to see the end? Okay. So let's move this up a little bit to see it. Now what I've got is negative x multiplied by x minus 6 to the second minus 4 minus x times x minus 6 times x minus 2 divided by x to the 4/3 multiplied by x minus 6 to the 8/3. I can take away 3 of these, make that a 5. I could take away one of those, and that one is now gone. So in my numerator, I now have negative x squared plus 6x, and then I can distribute those. That would be 4x minus x squared plus 2x minus 8. So just to make one person happy, I'm going to take this negative that's right here, and I'm going to put it at the front, right here, okay? So now that'll be positive. Will that make you happy? There. Okay, so plus, and now I've already FOILed that out, so that would be plus negative x squared, that's positive 2x and positive 4x plus 6x, and then minus 8, all divided by x to the 4/3 times x minus 6 to the 5/3. We are almost done. Positive x squared cancels, negative x squared cancels. Positive 6x cancels with, that's supposed to be negative 6x. What happened?
That one right there was supposed to be negative 6.
Oh, the first one is negative 6x right here. That's a negative 6x right there, not a positive 6x. So this is negative, so it goes there. That 6x cancels. What am I left with? I'm actually going to be left with a negative 8 because it's the opposite of 8, so this is going to cancel out. And what do I end up with as my second derivative? And yes, this is the end. Great job, everybody. All the extra help. X to the 4/3 times x minus 6 to the 5/3. Now we have our second derivative, so now we can take the first and second derivative tests.
We're still not done.
We're out of time.
Oh, no.
It's okay, I didn't give you anything this difficult.